Hey guys, in this lecture we're going to talk about the conservation of momentum. And what this law tells us is that the total momentum, the sum of all momentum vectors in an isolated system cannot change. And so the key here is understanding what an isolated system is. And it's kind of an abstract concept. So to illustrate this, let's look at the example of an airplane. So if I have an airplane flying, I can define my system as just the solid metal plane. The only momentum in that system is just the planes. And that momentum cannot change unless energy leaves the system or is introduced from outside the system. And if that happens, then our system isn't isolated, and that rule is violated. So in this example, the plane could burn more fuel and propel more gas from its engines to move faster, and this would cause the plane's velocity to increase, which would increase its momentum. But the gases and combustion products are not part of the system. We've excluded them. The plane's momentum could also be changed by some outside force. It could be hit by a meteor or a 2K-12 Cub surface-to-air missile. Again, all of those scenarios involve something outside of our system. So by isolating it, we've precluded any of that from happening. The momentum cannot change. Now, we could include the gases and combustion products as part of our system, and in that case, the momentum of our system would be the momentum of the airplane plus the momentum of the expanding gas and the combustion products that are moving from the engine's turbines. And in this case, the sum of all these momentum vectors should equal 0. And we can add as many objects to the system as we want. We can have a guy parachuting out of the airplane. We can have the surface-to-air missile about to impact the airplane. And the sum of all of these momentum vectors cannot change. A common scenario where the conservation of momentum is applied is in collisions. And so in the case of a collision, our system is usually just defined as all of the objects that are colliding. So I might have like two billiard balls moving towards each other, or I could have several masses that are all moving towards some larger mass. In any case, if I sum all of these momentum vectors up, this vector sum has to be the same before and after the collision. And there's two types of collisions that we generally talk about. Elastic collisions, you can imagine two things that collide and kind of bounce off each other. And what defines an elastic collision is that momentum is conserved, but also kinetic energy is conserved. And this is not true for inelastic collisions. So in an inelastic collision, you think of something that hits an object and sticks to it, and after the collision, the two objects are moving together as a single object. In this case, momentum is still conserved, but energy is not. And so the mathematics for solving elastic collisions is usually a little bit trickier than inelastic because you have to use both conservation of energy and conservation of momentum in conjunction with each other. But inelastic collisions work out a little bit easier. Let's look at an example of an inelastic collision. Okay, let's say we have a car and a truck that are moving opposite directions towards each other. Say the mass of the car is 1,800 kilograms and the mass of the truck is 2,400 kilograms. And we'll say the truck is moving at 22.5 meters per second. So anytime I have a collision problem, I always want to draw a diagram of what my isolated system looks like before the collision and after collision. And remember that the total momentum before and after the collision has to stay the same. It cannot change. After the collision, we'll still have the truck and we'll still have the car. And now they've basically combined into a single object. And the combined car truck object is going to be moving to the left at 3 meters per second after the collision. And so we need to find what the velocity of this red car is before the collision. And to do this, we will use conservation of momentum. Remember, the total momentum of this system before and after the collision has to be the same. And before we get started, we need to define a coordinate system. So I'm going to let the left be positive and right be negative. So any velocities or momentums that are moving to the left are positive. Any velocities or momentums that are moving to the right are negative. So let's start by finding the momentum of the blue truck. It's moving to the left, which we've defined as positive, so its velocity and momentum are positive. And its momentum is just its mass times its velocity. It has a mass of 2,400 kilograms, a velocity of 22.5 meters per second, and its momentum is just going to be the product of those two things, which is 54,000, and our units are kilogram meters per second. Okay, next let's look at the momentum of our system after the collision. So after the collision, we have essentially a single mass, which is going to be the sum of the mass of the car and the mass of the truck. So 1,800 kilograms plus 2,400 kilograms, which is 4,200 kilograms. So that is the mass, and we were given that the velocity of this mass is 3 meters per second. Again, that's positive 3 meters per second because we've defined the left motion as positive. So the total momentum of our system after the collision is just going to be the mass, 4,200 kilograms, times the velocity, just 3 meters per second, which is 12,600 kilogram meters per second. And so, again, that's the total of momentum of our system after the collision, and the conservation of momentum tells us that this must be the total momentum of our system before the collision. So I know that the momentum of this red car, when I add it to the momentum of this blue truck, it should be 12,600 kilogram meters per second. So I can basically write this as an equation, and if I subtract 54,000 kilogram meters per second from each side. Alright, this workspace is getting a little bit crowded, so let me clean this up a little bit. And that gives us 41,400 kilogram meters per second. That's negative 41,400 because the car is moving to the right, and we define right as negative. So that is the momentum of the red car before the collision. So now we're almost done. We were looking for the velocity of the red car, and we know its momentum and its mass, and so we can solve for the velocity pretty easily. We just divide the momentum of the car divided by the mass of the car, and that will give us a velocity of 23 meters per second. Actually, negative 23 meters per second, since the red car is initially moving towards the right. All right, let's look at another application of conservation of momentum. This is not a collision problem. This is, I guess, more of a propulsion problem. We have a archer, and he is standing on a frictionless surface. So we'll say it's ice. And he has a bow and arrow with the arrow drawn and is ready to shoot. So let's say the archer's mass is 85 kilograms. The bow that he's holding is 3 kilograms, and the arrow is 0.25 kilograms. And so just like we did for the collision problem, I want to draw my system before and after the arrow is released. Now we're also given that the velocity of the arrow after it is released is going to be 75 meters per second. So after it's released, we have the arrow moving at 75 meters per second to the right, and our archer moving at some unknown velocity to the left, and that's what we're trying to find. And so again, the key to this problem is the conservation of momentum, and the momentum before the arrow is released has to be equal to the total momentum after the arrow is released. And our system is this guy, his bow, and his arrow. So what's going to happen is when the archer releases the arrow will fly to the right with some velocity, and that is going to propel the guy standing on the ice backwards to the left with some other velocity. Again, that happens because we're neglecting friction. He's standing on a frictionless surface. So the momentum of our system before the arrow is released is trivial to calculate. The archer is not moving, he's standing still, and the arrow is not moving. It's just notched on the bowstring. So we can sum all the masses of our system together, but it's a trivial problem because there's no motion, and so we're multiplying our masses by a zero velocity. So our initial momentum is just zero. There is no momentum before the arrow is released. Now, after the arrow is released, the arrow will have some momentum to the right, and we can calculate that. Remember, momentum is mass times velocity. The mass is 0.25 kilograms, and the velocity is 75 meters per second, and that gives us a momentum for our arrow of 18.75 kilogram meters per second. Now, since our total momentum of the system can't change, and we started with a total momentum of 0, then we know that the momentum of the archer and his bow after the arrow is released plus the momentum of the arrow has to sum to 0. So the momentum of the archer and his bow after the arrow is released is going to be negative 18.75 kilogram meters per second. Again, those two vectors have to sum together to equal 0, the momentum before the arrow is released. Since we know the archer's momentum and the mass of the archer and the mass of the bow, we can calculate the archer's velocity. Remember, momentum is mass times velocity. The mass is going to be the combined mass of the archer and the bow, which is 88 kilograms. And the momentum we just calculated is negative 18.75 kilogram meters per second. So I can solve this equation for velocity, and I should get about 0.21 meters per second. And this, I didn't write it here, but this should actually be a negative 0.21 meters per second. We define right motion in this case to be positive and left motion to be negative. So this answer should be negative 0.21 meters per second.